So for problem number 4, this is really, I say I want the angle of elevation of the sun in this picture. If you actually look, I'm really just saying solve for theta. So the easy part here, if you're familiar with trig, is that the tangent of theta is 24 over 15. And let me just kind of explain once again, I'm using the notion of SOHCAHTOA, which I know you've just had in geometry class. So we have the adjacent, the hypotenuse, and then the opposite here. I like to start here and go in alphabetical order if you don't remember it. So here's the adjacent side, then you go to H, then you go to O, so that's how you label the triangle. And of course we're using SOHCAHTOA, which most of you seem pretty familiar with. That being said, you're a little new to it, so I'm not going to be asking you at the level of detail that you would do in a geometry class. Now, to get theta, what I'm going to actually do is take the inverse tangent, or the arctangent now, of 24 over 15. And when I go ahead and do that, what I'll end up getting is about 58 degrees. All right. Now we have the planet Mercury. It has this diameter, and we have the true distance. And we want to know the scaled distance if we reduce Mercury's size to 3.5 centimeters in diameter. So we're going to do exactly what we did in the first lab of the year. Let's get the ratio of the total distance to the diameter of Mercury, and that will then give us, like we discovered in the lab, that'll actually tell us the number of Mercury planets that will fit between Mercury itself and the sun. So when we do that, we end up getting a pretty big number, something around
tomorrow in the same city as
12,260 Mercuries fit in between. So Mercury diameters is what I would say. And so if we want to know how long that is, we're just going to multiply by the distance. So 12,260 times 3.5 centimeters, and that's going to end up giving me 42,910 centimeters. There we go. All right, so that is the second page, and we'll work out page number 3 in the next video.